data that's, if there's too many routers in one location, we cleanse them. If the data was somehow didn't make sense, like being in the lake, we cleansed it, which removed about 3% of our data points. Okay, so it doesn't seem to have a huge effect, short of going out and No, it's a good question. You can imagine, but then what would they connect them to?
Yeah, so all this blue stuff, they're actually...
Yeah, they're actually routers. And if you go to Wiggle, you can actually go down and see and zoom in, and you can see the SSIDs and whether they're encrypted or not encrypted. Okay.
I know that some of my students found their routers there.
Oh, I'm sure.
And it was the correct answer.
So, so on average, the Wiggle.net routers have, on average, at least 10 observations. Okay, so you can look at the number of unique routers they have in Wiggle, and you can look at the number of actually contributed observations, and it implies that each router, on average, has been observed 10 times. In practice, probably the routers in cities have been observed a lot more frequently than the routers in the middle of the cornfields. So it's actually probably, for big cities, a much more accurate map than it is elsewhere. Okay, so here we see the giant components for different sizes of transmission radii. So obviously, the farther you can transmit, the bigger you expect the component to be, because the more neighbors you can talk to. Right? So what we did is we looked at the 45-meter case, and we wanted to see on this graph, okay, how far is the epidemic going to spread? We have to define some some rules of how the malware spreads from router to router. I can't just assume that all routers are vulnerable and you can just spread from one router to all neighboring routers, right? It's not fair. It's not a fair game, because some people do have strong passwords. Some people are using strong cryptographic algorithms, not WEP, but WPA. So we need some sort of way of modeling this. So we use a modeling technique from biological modeling, for modeling things like flu or Ebola or something. So there's something in that literature called the SIR model, which stands for susceptible, infected, and recovered, removed. So basically the idea is there's 3 states you can be in. You can be susceptible to be infected, right? You can actually be infected, in which case you can infect other people. And you can be recovered / removed. So for some diseases, you naturally recover and then are immune, all right? Like chickenpox, you generally don't get that twice. Or you die, right? And you're not going to get infected anymore at that point either. So what you can do is you can go from susceptible to infected, and you can go from susceptible to removed, or you can go from infected to removed. Okay. Someone who would go from susceptible to removed could also be someone who, for instance, got a flu shot. Okay, so that's why you have those ability for dynamics. So what we have to define is how you can go from these 3 states and which routers belong in which of the 3 states. So let's start off with the removed routers, the ones that aren't susceptible. We're going to assume that anyone that's using WPA encryption, okay, which is the cryptographic protocol that secures communications, it's the newer one, is not breakable. So we're going to assume that cryptographic protocol is not breakable, and so those routers are not susceptible to attack. This is actually a conservative estimate, because there is an attack on this protocol. It's just harder to do, and it was a good starting point for modeling. Okay. So from our data, we actually know who uses encryption, which routers have encryption turned on and which ones don't. Unfortunately, we don't know which encryption they have turned on, because that's not recorded. So I can look at a router and say that router's got either WEP or WPA turned on, but I don't know which. So what we have to do is we have to basically guess. So what we do is we look at the wild population and figure out what rate you see WEP versus WPA encryption. Turns out to be around 30% use WPA and 70% use WEP. And so what we do is for every encrypted router, we flip a coin to decide whether it was using WEP or WPA. Okay, if it was using WPA, we remove it.
So I have another question. 30%, you said that you look at some data. What data, or are there any papers? Or
we basically went around with our own router, and we saw, once we had something like 700 spots.
So this was in Bloomington?
This was in Bloomington, and then there's a group in California who wrote a paper, and I can't remember their names, but they actually came out, and their data was within 2 percentage points of ours, so we didn't worry about it. Okay, so as I said before, WEP's easily broken, so they're not removed. Okay, they're going to be later, and they're going to be susceptible. The other group is assuming even if you had no cryptographic protocol guarding your communications, that doesn't mean you can actually log on to the router to infect it. You need to be able to get through its administrative interface. And some people are going to choose strong passwords, either by luck or because they're people like yourselves who are security inclined and probably have a better idea of what to choose. Okay, so we're going to assume that some routers have strong passwords and they can't be broken into. I'll say more about that in a second. Okay, so the next thing we want to know is who's susceptible. So we're going to assume people with default passwords are susceptible. Okay, so we're assuming they don't have WPA by default because we've thrown them out. Other than that, we're going to assume they have a default password that's susceptible. The problem is we can't figure out what the default usage rates are for passwords. Why? Well, it's against the law in the US to log into someone's router, even if it's to check to see if they have a default password. Okay, so the University Council came in and said, no, there's no way you're doing that experiment. So we had to use a proxy. So the proxy is if the people didn't go to the effort of changing, say, their default SSID, which is the name you see broadcast from routers, we assume they didn't go to the effort of changing their password. Now, this isn't exact, but of course there's going to be some people who change their password and don't change their SSID, and there's going to be some people who don't change their password and change their SSID. So we figure it's a good proxy. We have no way of measuring it. But of people we've talked to, they all sort of think it's reasonable. So here's some different cities. San Francisco, Seattle, Chicago, North Indiana, which is actually West Lafayette, okay, South Indiana, which was supposed to be Bloomington, but it was Indianapolis for basically the reason that when we downloaded the points, we assumed South Indiana didn't include Indianapolis, but it turned out it did, and by that point we'd sort of moved on. So Manhattan, so it's not just New York, it's Manhattan proper, more or less, Boston. And so of these cities, you can see of the popular sort of 4 companies of routers, you can see the rates of the default SSID in those cities. Okay?
So basically this means that on average, Belgium is the one with the highest number of default SSIDs? That's what it means?
Where do you see? No. So this is the opposite. So it means of the routers, 0.34% in San Francisco have the default Belkin 54G SSID. So we're assuming 0.34% of the routers in San Francisco have are susceptible under the Belkin 54G default.
So then on average, for example, Belkin 67% of them.
So 0.67. So
0.67.
this is not normalized for the fact that Linksys is much more popular than Belkin, because we don't actually care which manufacturer. I don't care if Linksys is more popular than Belkin. What I care about is how common are default passwords. Okay, so it looks like Linksys is much worse than Belkin, but that doesn't say anything about the two companies other than the fact that probably Linksys, this is probably better as marketing data for Linksys than anything else. Okay, so that's the first case. So we assume you're susceptible if you have a default password. Is it advancing? Okay, so the next thing we have is weak passwords. So we assume that about 25% of the people who change their passwords, about 25% of the people are going to choose a password that's in a small dictionary of about 60,000 words. Okay, this is based on some work done by a Klein that where he actually looked at the passwords people used in an experiment, and he basically came up with a list of about 60,000 words that contained about 25% of people's passwords. Okay. Then the next susceptible group we have is people who have medium strength passwords. And so what we're going to assume is there's another 11% of the people who have passwords that aren't in such a small dictionary, but are then in a much larger 1 million word dictionary. Okay, and this is again based on experience of different malware that's gone around the internet that have done brute force attacks, their success rate and their infection rates. So the only other thing we have is if the router is using WEP, so this is the other cryptographic protocol that's broken, we have to spend time to attack it. In other words, to break the cryptographic protocol. So any router that uses WEP is going to conceivably be susceptible, and if it doesn't use WEP, if it's got a weak password or a medium strength password, it's going to be susceptible. Okay, so previously I said that routers with strong passwords are not susceptible. Okay. And then we have to say something about infected routers. So we're going to infect some routers at the beginning just to start the